All right, let's take a look at exam 1, what was on it. It'll be similar things again. Here's the first page. Now, this first page is getting at all these questions on this first page are really just, do you know what a differential equation is? I mean, that's the way you want to think about it. So the first one, it says show that the circle x squared plus y squared equals 16 solves the differential equation y prime equals minus x over y. Well, in this case, then, if you know what a differential equation is and you have this implicit function here, then one way to solve any equation, really, whether it's algebraic or differential or an integral equation or something like that, is you simply plug in your candidate solution to see if it solves this differential equation. And in this case, the easiest way to do that is just use implicit differentiation to see that it should work. And so, I'd have 2x here and then plus 2y, y prime equals 0. And, if I solve for y prime to see what it is, actually, you end up getting exactly that differential equation. And so once you solve for y prime, you would say, well, if I substitute y prime in here, which is minus x over y, it does equal minus x over y. So it's just plugging in our candidate solution into the differential equation, but for a differential equation, to plug it in, you have to take a derivative. Euler's method, again, really, because of what Euler's method is, it's really getting at, do you know what a differential equation is telling you? And this dy dx is telling you the slope at any given point. And then all Euler's method is using the tangent line at a given point. And so we're given our first point, 0, 1, because it's y of 0 equals 1. And we're given the slope if we plug 0 and 1 into it. And so I can determine the tangent line, and we've known how to do tangent lines for a long time, and we can then get an estimate of what the y value would be at point 1, because I have a tangent line, and I just plug in point 1 into that tangent line equation, and I will get a new estimate for y. I know where I am because that's the x value, and I do it all over again. I make a new tangent line and go, and that really plays to, do you know what you're looking at when you see dy dx equals this stuff? And you're just given a slope. It's a slope for the function y, and it's, in this case, an implicit definition because we've got y in there, but that's all it is. It's just a slope. And so if I have a slope and a point, I can tell you what the tangent line is, and that's all Euler's method is doing. And so when you go back and look at that, that's what you want to think about. Phase plane again. The idea here is at each point I can get my dx dt and my dy dt, in which case my slope then is the dy dt over the dx dt, and I can just draw a line with that slope. And so once again, the question is, do we know what we're looking at when we see this dx dt equals x minus y? That is just the rate of change of x with respect to t, rate of change of y with respect to t, and we know from calculus 2 that we can get dy dx just by taking the ratio of dy dt and dx dt. And then we just draw a picture of it as a slope. The same sort of thing here, draw the slope field, and the phase plane, again, this is just vocabulary. Do you know what those things mean? And if you know what those mean, it's just not a big deal. I factor the equation for you and so forth. So if we want to talk about a phase line at the left, then if we know what that means, then we know that what we're looking for are the zeros of this right hand side. Well, that's pretty easy. Y equals 1 and y equals negative 1. I can mark those on here, and then I just ask, well, there we go. What's the sign of this function when I'm in between those things? And again, well, I'll plug in 0. I get 1 times 1, that's positive. So in between minus 1 and 1, I know it's positive. And if I'm above 1, I can very quickly see it's negative, so I draw that line down. And so again, it's just saying, do you know what you're looking at? Do you know the definitions of these things? And so the calculations are very straightforward. And again, I'm not out to make these difficult calculation problems. I want to see that you've read the material, you've done your homework, and so you know what these words mean. Okay, and so here is a calculation, or a bit of a calculation. You have to do that substitution, and this gets into more of it's a straightforward algorithmic calculation. You do the same thing every time, but it gets a little tougher because you are doing some algebraic substitutions and you have to keep things straight. Again, you practice it lots and lots, and it becomes much simpler because you just do the same thing every time. It's very algorithmic. Now here, these two modeling statements, yeah, these are hard. Now, way hard? No, I don't think they're way hard. I expect people can do them, but generally speaking, what I find, even among reasonable mathematicians, even very good mathematicians, is they aren't very good at going between a physical or possibly conceptual situation where we're talking about it in English and it's not framed as a mathematical problem typically. I find people aren't that great at that comparatively. Certainly mathematicians are way better at it than non-mathematicians, again, generally speaking. At this level, when you're talking differential equations and so forth, because you have to know what a differential equation is. But these are harder problems, and so they do take a little more thought, and they're not, they're not just oh, wow, if you read this, obviously this is the answer. Well, no, I don't think that. Here, though, you have to know what some English means, the rate of change of x with respect to t. Oh, dx dt, okay, is proportional. Okay, that means that one quantity is proportional to another, like y equals kx, where y is one quantity, x is another, and k is the constant of proportionality. And then to the ratio, oh, I know a ratio is a fraction, x over t. So I do have here dx dt is equal to some k times x over t. Okay, so not bad. This one's not bad. Pretty straightforward. It's using mathematical language for the most part as our real world language. Not so bad. Here it gets a little worse. Find the family of curves. Ooh, a family of curves? What the heck does that mean? Well, that would be like, y equal mx plus b is a family of curves. It's a family of straight lines. So it gets a little tougher there, such that the concavity at each point, okay, now I've got to think, okay, that's the second derivative of my function with respect to the independent variable. It doesn't say what those are. I can pick, I could go with dy squared over, or d squared y over dx squared, something like that. But it's the concavity at each point is equal to the square of the difference of the coordinates of that point. So I've got to think about the coordinates of that point, and okay, that's an x and a y. The difference of that, x minus y, or is it y minus x? I don't know, but it turns out, well, it says the square, so it doesn't matter. And so I get something like, y double prime is equal to, say, y minus x quantity squared. Something like that. But those, I think, 6 and 7 are much harder problems. In 8, you're just given a bunch of differential equation situations. Now, they're really, one could argue, I guess, that there are 2 types of problems here. They're either separable, okay, so we can get it either as y prime times a bunch of stuff involving y equals a bunch of stuff involving x. That's the case here with b, I believe. We should be able to separate this just fine. Or it's the integrating factor idea, which is simply you look at whatever's multiplying. I look for y prime plus or minus something involving x, or even just a constant times y equals a function of x, and I just look for what that function is, 1 over x, and I have to do my algorithmic integrating factor. So I just do that, and that's how I solve that problem. It's one of those 2. Now down here, again, this is where I say you could argue that there's only 2 types here. This looks like a third type because it's a system, but actually it is simply one of the other 2 types in succession, or maybe both of the other 2 types in succession. Because notice it's x prime equals minus 2x. Oh, that's separable. I solve that first differential equation. I get x as a function of t, and then, or z, or whatever. It's just not y or x, because it's x prime and a y prime here. So there must be some third variable that I'm talking about. I can solve that first equation, and then once I know what the function x is in terms of t, I could plug that in here, and now I get y prime equals some function of t plus y, move the y over to the left hand side, and I can do that as an integrating factor, because I'll have y prime minus y equals some function of t. So, you can argue that, yeah, this is a third type because it's a system, but at this point in this exam, we only had the case where these were at least partially independent, in that I could solve one and then plug that in for the other one in order to solve that one. Okay, so then we get back down here to 9. 9 is, again, a definitional kind of thing. Give the order. Well, it's y triple prime, so it's order 3, and then is it linear or nonlinear? And, well, I just have to look at the y's, since that's what I'm taking the derivative of, and I see that all the y's are simply some derivative of y or y itself, nothing like y squared or the square root of y or 1 over y or anything like that, so it's linear. It doesn't matter that, of course, that I've got x to the 5th or x squared over here. And then finally 10, again, it's a particular type of problem that they gave us in the text that we looked at, and there are other types. There were, the spring problems and so forth. So we had some different types of problems that they gave us, but this was one and it was a modeling problem. And again, the modeling problems are harder in general for most people. Not all, but most. And so, you know, it's more likely that you would need to practice this quite a bit more. Now, you know, again, it's one type they've given us. And so the way you prepare for that is, well, you look at those and you do a lot of those, and you look to see, you know, what's important in these. You know, how is it they tend to solve them? Now, you know, any given real problem might not exactly fit it. Now, for us in our exam, yeah, we fit the book problems. But in reality, you know, some little thing could be different, and so, you know, it can get very difficult at that point. But here, the idea is that we tend to solve these the same way every time. These are sort of like a population problem. In this case, it's the population of salt, and we tend to work with it by concentration. And we know we often, you know, we can look at these by rate of change. That turns out to usually be the easiest way to look at the relationships. And so the rate of change of the salt is going to be how much salt is coming in minus how much salt is going out. Okay, so we've got our rate of change of salt, say dx dt, or whatever you call the amount of salt, you know, say it's x and then time for t. But then that rate of change is, you know, pretty simply how much is coming in and how much is going out. But that's, when I say how much, you know, it's a rate. You know, at what rate is it coming in, and at what rate is it going out? Oh, well, it's coming in at 1.5 pounds per gallon. Oh, but you see, that's a problem because I said dx dt, and so those units are like pounds of salt per unit time. And so you see I have 1.5 pounds per gallon. Okay, well, then we have to figure out, well, let's see, oh, into the tank at 3 gallons per minute. Well, if I take 1.5 pounds per gallon, 3 gallons per minute, the gallons disappear, those units, and I get 4.5 pounds per minute. Oh, that's the right kind of units, and that's what's coming in. And then the harder part usually for these is what's going out, because we've got this 100-gallon tank that's half filled, so I've got 50 gallons in there. So the water comes in, and then it goes out at a rate of 2 gallons per minute. So it's the gallon. So you see, it's going in at 3 gallons per minute, going out at 2 gallons per minute. Every minute, I got another gallon in there. And so the outflow gets a little bit harder, okay? But that's what this problem is. So this one's a little bit tougher. But as you look at, when you look at this first exam, you know, you want to think about it as these are really definitional kinds of things. Know your vocabulary. Okay, know your vocabulary and know it's important. You know, you were allowed, now when you do a retake, you'll have your notes and all that, but you are allowed a 8.5 by 11 sheet of paper. And so what you want to do is look over each of these types of problems. Don't get sucked into the specific problem per se. You want to think of, like these in number 8, as what type were they? Were they separable, or were they an integrating factor? How can you tell? You know, what is it you do to decide which is which? And then, you know, how can you go about solving them? And, you know, those are the kinds of questions you want to ask. I'll try to do some more, a little bit more video with, you know, some of the key points on some of these. But in the end, you need to ask questions. If you're not asking questions, you're not thinking about how to get it done. Now, or you know exactly how to get it done, and so you have no question. Well, that's fine. But if you're looking at things and you're unsure, like, well, how would I? I'm stuck. I don't see how to separate the variables, because again, you're either going to separate the variables or you're going to use an integrating factor. Okay, well, what is it? Oh, and I'm sorry, I see this x double prime minus 2x prime equals 2. So, and actually, I jumped into this video. I'll have to look back, but I think on this one, this was meant to be a harder one. On this first exam, I don't think we've done second order equations yet, other than to rewrite them as first order equations like we did up here. And so I don't think that was the point on this one. I think on this one, the point is that if I look at this as, instead of solving for x, solve for x prime, right? Call it y or v or something like that, and say v is x prime. In a way, you're rewriting it as a system, but it's a system you can just solve. So you'll get v prime minus 2v equals 2. Okay, and then v of 0 is 1. So I think that was probably how that was supposed to be solved under what we knew how to do at the time. I suppose at this point you know how to solve a second order equation, and so you could, but at the time I believe this was a harder one. These were supposed to be straightforward, these first three and this last one. Pretty much, integrating factor, separate variables, and then here you separated variables on that first equation, and then once you solved that, you plugged it in here, and then that one would have been an integrating factor. So this one you had to do 2 steps. This was meant to be a hard one, and the reason, you had to, under what we knew, you would have needed to think about doing that substitution. And now we had that, because like back here again, rewrite this as first order system. Well, so you rewrite that as a first order system, and that you could have solved. Okay. So again, the big thing is you need to look at work. You need to ask questions, and I can put some things out there, but I did that the first time around, and I didn't get many questions. So you need to absolutely be asking me plenty of questions, and I am very, very happy to answer them. But we want to get you going on these and get you confident, so that you feel like, hey, I can get 100% on this baby. And there's no reason why you shouldn't get to that level of confidence. Okay? So this has gotten to be a pretty long video, but you have to look at these pieces as just what they are. Mostly matters of definition and a couple of techniques, and then you have to practice and you have to ask me questions if you're having any trouble whatsoever. And again, I am very happy to answer questions, but if you don't ask, I really can't answer, because I'm not sure what you need. So please, please, please ask questions. Thank you.